Our next speaker is Prabhakar Ragde, who is responsible for many, many, many happy hours for me of walking in small circles and staring at the ground, trying to figure things out. So thank you for that, and I look forward to more.
So since Matthew Butterick is here, I feel compelled to apologize for the use of Helvetica on my slides. Proust is named after the French novelist Marcel Proust, but my program has nothing to do with French literature. The only connection is that if you say proof assistant really quickly, it sounds like Proust. Here's Matthew. So Matthew, I apologize for the Helvetica. Please forgive me. So oh, the aspect ratio is off here. What's going on? Does anyone know?
The font.
Yeah. Yeah, there we go. That's a little better. So Proust is a series of small Racket programs that are to be used as proof assistants. I wrote Proust to understand what proof assistants do, but after writing it, I realized that I could use it for another purpose, which is to teach a required course at the second-year undergraduate level in logic and computation. Now, we've been seeing lots of great Racket features here, and Proust doesn't use any of them. What Proust does use is pretty basic. S expressions for the surface language, so that parsing is trivial. They're parsed into an abstract syntax tree built of structures, and then I use match to do structural recursion on the abstract syntax tree, and format for pretty printing. I'm not even going to show you any Racket code, because you could have written Proust yourself. That's the point. I don't give Proust to my students. I give them the basic design, and they do most of the implementation. And then they use the tool that they wrote to do their homework. I think that Racket has shown us that ideas that people thought were difficult can actually be easier to understand than ideas that people believe to be simple. For me, many of the epiphanies of how to design programs were of this form. You can give students a precise semantics for the programming language they're using in an introductory course. You can talk about recursion in a way that makes it easier to understand than iteration plus mutation. You can talk about functions as values. You can do all these things if you have the right language, the right mental models, and the right attitude. And it's that spirit that I was trying to bring to the teaching of logic. So what goes wrong? Let's take a look at a conventional approach. This is the outline for our course. And to be honest, the course that I run using Proust does more or less the same thing, but in a different fashion. We start with propositional logic, which is made up of variables plus the logical connectives, implication, if then, and, or, and not. We then go to predicate logic, which adds the quantifiers for all and there exists. We add a way to talk about equality and a way to talk about mathematical objects such as the natural numbers. All of this is a standard math course, and the computation part comes in at the end, where unfortunately we tend to use a simple imperative language and use something like Hoare logic to prove things about programs written in that programming language. I have tried doing it that way a few times, and despite my best efforts, the students complain. They say, well, you know, what's in the course varies a lot depending on who's teaching it, because we can't help but sneak in our pet topics. I've seen other instructors talk about circuits, about artificial intelligence, about biological computing, and I confess that my weakness is for meta-mathematics and model theory and complexity theory. After the informal, or what they thought was formal, treatment in their math courses, they find formal logic confining. And it's not that interesting to them. There's no connection to the rest of what they're doing in their computer science courses. And when we finally get to computation at the very end, it takes so much effort to prove the simplest things about the simplest programs that they conclude it's of no use to them whatsoever. Now, these are valid complaints, and I wanted to try to address them. So here's an example of the kind of thing they're doing. This is a conventional proof of it's a proof of the thing at the very bottom, which is the propositional formula. It says A implies B implies B. And what we see above that is a proof tree built from the application of inference rules that govern how we introduce implication and how we eliminate or use it. And despite the fact of the existence of provocative named rules like ass, it's not that compelling to students. Now, the trees are awkward, and typically we have some sort of linearization of this, but that just changes the aspect ratio. It makes it tall and thin, but it doesn't change the content. And this formalism is not very compelling to them, but there is one formalism that they not only tolerate, but they're positively enthusiastic about, and that's a programming language. They like to program. So you can see where I'm going with this. We need to make proofs look more like programs. If we view a proposition as a type, and we view a proof of that proposition as a program that has that type, then we have proofs as programs. And this, of course, is the Curry-Howard correspondence, and it's typically considered too difficult for a second-year course. But maybe not. So let's take a look at an example of this for implication. What is a proof of T implies W? It's a function that consumes a proof of T and produces a proof of W. This corresponds to what we do in informal proofs. What do we do to prove T implies W? We assume T, and we use that assumption maybe several times to prove W. Now, that's not a self-contained proof of W because of all those assumptions. But if someone gave us a proof of T, we could stick it in at all those points where we assumed T, and that would be a self-contained proof of W. So that informal proof really is a function that consumes a proof of T and produces a proof of W. So applying this to what we proved previously, if we want a function has type A implies B implies B, anyone who's gone through a first course using how to design programs knows how to write this. Well, you need some value x of type A, and if you have a function f that takes a's to b's, you just have to apply f to x, and you get a value of type B. So the proof term is lambda x, lambda f, f applied to x. And that's, first of all, more intuitive, and second of all, a lot shorter than the proof tree. Now, you have to check that this is valid, and the checking rules are basically the conventional inference rules interpreted as type checking rules. And the type checking algorithm, if you run it on this example, its call tree is going to be the proof tree. So the proof tree is implicit in this proof term. It's just that the algorithm for checking it does all the boring work. And that's what we created computers for, to do the boring work for us while we do the interesting stuff. So Proust is made up of, Proust uses this idea, except I throw in a few more parentheses to make the parsing trivial, but it's basically this language. And we have a parser to parse those terms into an abstract syntax tree. We have a printer to go the other way. And two mutually recursive functions that do type checking and type synthesis. You may have noticed that my lambda terms, my proof terms, don't have any type annotations in them. So sometimes we have to figure out what type is represented by a term. And that's the type inference part. This is all syntax driven so that the code is really simple once the rules are laid out. Students can start with an incomplete program, an incomplete proof, and successively refine it in the interactions window of Dr. Racket using the read evaluate print loop. That's the assistant part of a proof assistant. Well, that works for implication, and for each of the other logical connectives and or not, we get natural programming constructs. We get pairs, we get tagged unions, and for contradiction, we get the empty type. For each of these, we, the students and I, interactively work out the rules in lecture because we're working from their intuition towards the rules. And then the students, as part of their programming homework, implement the rules in Proust, and then they use the tool that they wrote to do proof homework. Well, that works fine for propositional logic. But propositional logic isn't the problem with a conventional approach. It works pretty well there, too. Where the wheels fall off the bus in a conventional approach is when we hit predicate logic, when we introduce for all and there exists. Conventional predicate logic is first-order logic. That is, we quantify, we say for all x, but we don't say what x is. We quantify over some unspecified universe. What the universe is shows up in the semantics, in the interpretation. And there's no way to nail that down exactly in the language of logical statements. Proust, on the other hand, uses higher-order logic, which is what we do in informal proofs. We don't say for all x, I'm not telling you what x is. We say for all natural numbers n, or for all strings s. We specify the domain of quantification. And higher order because we want to be able to do things like quantify over all functions. That's what calculus does. Quantify over relations. Quantify over types. That gives us polymorphism, which is very useful. So Proust uses higher order logic, and the domain of quantification is specified. Let's see how this will work with for all. So a proof of for all x of type t, some statement W holds, and W here is a statement that could mention capital X several times. And such a proof would be a function that consumes an object little x of type t and produces an object of type W, except W where every time the variable capital X is mentioned, it's replaced by the specific object little x, substitution. Now, what we have here is a lot like a lambda, a lot like t implies W, except that the return type of the function can depend on the argument to the function, little x. It can depend on the value of that argument. That's called a dependent type. And that's considered an advanced concept. In Pierce's book on types in programming languages, it's at the very end. So in my optional fourth-year course on programming languages, if I race through the book, I can talk about dependent types in the last week of lectures. So why am I talking about it a third of the way through a sophomore course? Because in a conventional treatment of for all, it looks like this. The only thing that's missing is the t. We're not quantifying over a specific domain. So the substitution part is already present. That's the way for all works. And we're already taking elements of the universe and injecting them into our logical statements. In the propositional world, we could keep terms and types completely separate. There were different languages. They're on opposite sides of a colon. And now what's happening is the terms are jumping over that colon and landing in the types. They're all getting muddled together. We have terms, and some of the terms are types, but not all of them. And some of the types are propositions or logical statements, but not all of them. We could also have things like the natural numbers. First order, I think, views this as some sort of contagion or promiscuity and tries to limit the damage. But I think we should really embrace this fully because dependent types offer us a very expressive language, which makes our proofs more natural and shorter. So in order to do the work here, Proust has to, well, with for all, you have to have substitution. That's sort of the meaning of what's going on. And it has to be proper substitution. So You have to worry about free variables. You have to worry about variable capture. To avoid that, you sometimes have to change the variable. You have to do proper renaming. And then, well, if you've changed the variable, you might change a statement like for all x, x equals x, into for all y equals y. But those are the same thing. So you need a notion of equivalence that's sensitive to that. You need alpha equivalence. You need all these things in a conventional treatment. So we're not doing anything that a conventional treatment wouldn't do, except that in a conventional course, you don't tend to do an implementation. So people fudge the details or wave their hands or hope that students won't notice, but they do notice. The lack of it is going to affect them, the ambiguity, and it leads to confusion. To see this, you just have to give students a nested induction on the natural numbers. And watch them use the same variable n, because that's, n is a natural number. That's what you do induction on. You do induction on n. They'll use it for both the inner and the outer induction, and they'll get confused. They won't be able to complete the proof. This happens. They don't realize that for the inner induction, they should call their variable something else, like m. So we have to do all this work anyway. We might as well do it properly. And we need, because expressions are sneaking into logical statements, sometimes those expressions need to be simplified in order for equivalence to work. So we need a notion of reduction. But reduction is just substitution. We've already done the work for that. In fact, computation in the lambda calculus is just substitution. So we already have computation for free. We don't have to do anything extra. We don't have to introduce a new language and a new semantics and a new logic. We've been talking about programs all along. Now we get to run the programs. So the proofs continue to be more intuitive and shorter than conventional proofs. And it's not too hard to add new data types. In lecture, I show them how to add Booleans. And then as homework, they add natural numbers. And then they prove things about functions that consume and produce natural numbers, which they write themselves. Those functions can be written with the aid of polymorphic eliminators. If you make them strong enough, for example, an eliminator on the natural numbers can give both structural induction if when you use a natural number, you produce something that's a logical statement, you get structural induction. But if you produce another natural number, you get structural recursion. And the same mechanism, the same reduction rules work for both these tasks. We still have 3 weeks left at this point in the course. And so we move to the full-featured proof assistant Coq, which has a 20-year history and lots of great developments. I teach a graduate course where I spend a whole semester on Coq, and there's still a lot of magic. Students don't understand what it's doing. In fact, I tried to write Proust originally to understand something of what Coq was doing. But Proust demystifies Coq. And the students seem to take to it really well. And I have graduate TAs in the programming languages group who are using Coq for their research, and they tell me that much of their intuition as to what Coq is actually doing comes from Proust, comes from TAing this course. So that is really nice. The undergrads, they see Coq as, it's fun. They enjoy using it, and they can see that it's potentially useful. So in summary, Proust is a series of small, simple Racket programs which help in effectively teaching the ideas of logic and computation using the not-so-difficult concepts of proofs as programs and dependent types. That's my talk. Thank you very much. The question is, how do we allow students to add data types without introducing divergence? In order to add a data type, we have to talk about a representation, we have to talk about introduction rules, and we have to talk about elimination. And we have to talk about reduction rules, I guess, those 4 things. And the reduction rules are, typically the representation is, for example, for natural numbers or for lists, it's recursive. And you can, the reduction rules are structurally recursive, and they reduce down to the base cases. So I don't know if there's any way of definitely avoiding divergence, but in the examples we do, we have a natural way of avoiding it. I don't know if that answers your question. Matthias, you.
I want to ask a question. And do you teach about the law of excluded middle?
Yeah, so I didn't have time to talk about the fact that this is all intuitionistic logic. And
After you want to use continuations.
I'm sorry?
If you use continuations, you could teach the law of the excluded middle.
So the question is about teaching the law of the excluded middle, and the observation is that the computational interpretation, there is a computational interpretation which involves continuations. I'm not using continuations because I want to keep the program part as simple as possible for sophomores. But I do talk about, it seems to me that whenever we do an unconventional treatment, we always have to point at the conventional treatment and explain why we're doing things differently and how they can understand the conventional material if they choose to. So they're always looking at what their friends are doing in the other sections. And I talk about things like the law of the excluded middle. I say we're doing intuitionistic logic. We don't have the law of the excluded middle, but we can add it as an axiom. The only problem is that doesn't result in any problems except that there's no computational interpretation. So if it ever sneaks over into a program, you're going to have a problem. You can't run your program. That, I think, that seems to be good enough for them. Other questions? Yeah. Okay, so I sort of dropped out the code sizes. The earliest version of Proust, which I provide them, which is just implication propositional, that's about 80 lines of code. When you add in all the other stuff, and that's what they do, it comes up to about 200 lines of code. I provide them with the basic implementation of for all in the predicate world. And that's about 200 lines of code. When you add in everything else, we add in there exists, we add negation in. You could add the logical connectives back, but I don't ask them to do that because we moved to Coq instead. If you add everything in, it's between 400 and 500 lines total. So they do more than half the work. Yeah? They're mostly computer science majors. Now, we're in a faculty of mathematics, so some of them are doing joint degrees. I get a number of math students who are interested in the topic, and they can take that course without paying extra fees, so some of them choose to do that. I've run the course twice so far in this new version, and the conventional version is despised by our students. It's the most hated course. But my version, at least according to anonymous course evaluations, they seem to like it. So I think it's working pretty well, and I probably, by reputation, and I probably get the more mathematically inclined students, but it's hard to say.
Okay. Thank you very much.